There are moments in physics when nothing seems to happen. No explosion, no flash of light, no visible change at all. Just silence. But in science, silence is rarely empty. It is often the loudest signal that something fundamental is about to change. Across laboratories, observatories, and equations written on chalkboards late at night, researchers have learned to recognize this pattern right before a system reorganizes itself. Measurable activity drops. Noise collapses, variability tightens. The field goes quiet. In nature, this happens before earthquakes. In cosmology, it happens before phase transitions. And in quantum systems, it happens when probabilities narrow and outcomes become inevitable. What we experience as stillness is often the final moment before reality selects a new path. Today, we explore a provocative idea at the edge of modern science and philosophy, that when the field goes dead silent, when your inner and outer noise suddenly collapses, you may be standing at the boundary between timelines. Not in a mystical sense, but in a measurable, physical one, rooted in how the universe processes possibility, observation, and change. This is not a story about magic. It is a story about how reality reorganizes itself, and why the quiet moments matter more than the loud ones. If you enjoy slow, burn science documentaries that explore the universe beneath the surface, subscribe to The Boring Universe like this video, and leave a comment. And tell us which part of the country you're watching from. In classical physics, silence is no special meaning. A system either moves or it doesn't. A pendulum swings or it rests. A planet orbits or it drifts. But the universe we actually inhabit is not classical. At its most fundamental level, reality is statistical, probabilistic, and deeply sensitive to observation. And in this deeper layer of physics, silence is not the absence of activity. It is a compression of possibility. To understand why silence matters, we have to start with fields. Modern physics does not describe reality as a collection of solid objects moving through empty space. Instead, it describes a universe made of fields. The electromagnetic field, the gravitational field, quantum fields for every particle species. Even empty space is not empty. It is a restless background of fluctuating energy, virtual particles appearing and disappearing too quickly to observe directly. This underlying structure is sometimes called the quantum vacuum, but it is anything but nothing. A field is a mathematical description of potential. At every point in space and time, a field is a value. That value determines what can happen there. When physicists talk about the state of a system, they are talking about how these fields are arranged, how much energy they contain, how much uncertainty they allow. Most of the time, fields fluctuate. They ripple with thermal noise, quantum randomness, and environmental interference. This constant motion creates a background hum, a baseline of variability. But under certain conditions, that variability collapses. In condensed matter physics, when a material approaches a phase transition, something remarkable happens. As water cools toward freezing or as iron approaches its magnetic threshold, fluctuations slow down. The system becomes unusually stable, unusually quiet. Physicists call this critical slowing down. The system is not dead, it is poised. It is waiting to reorganize itself into a new structure. Silence in this context is not rest, it is tension. The same pattern appears in quantum systems. When an electron exists in a superposition of states, it occupies a cloud of probabilities. Its behavior is noisy in a statistical sense. But as the system interacts with its environment, through a process called decoherence, those possibilities collapse. The wave function narrows. The system selects an outcome. From the outside, this looks like a sudden stillness followed by a definitive event. From the inside, it is the end of uncertainty. This is where the metaphor of timelines enters the discussion. In quantum mechanics, different possible outcomes coexist mathematically until interaction forces a resolution. These are not literal parallel universes in the everyday sense, but they are genuine branches in the space of possible futures. When probabilities collapse, one branch becomes real. Others vanish. The field goes silent. Importantly, this silence is measurable. Physicists can detect reduced variance in systems approaching critical transitions. Neuroscientists observe similar patterns in the brain before moments of insight or decision. Neural activity synchronizes. Noise drops. The brain enters a brief, coherent state before reorganizing its internal model of reality. Silence precedes change. This pattern suggests something unsettling and profound. Reality does not always change gradually. Sometimes it waits. Sometimes it gathers itself. Sometimes it goes quiet and then it moves all at once. In cosmology, the early universe underwent a series of phase transitions as it cooled from the Big Bang. Forces separated. Particles acquired mass. Space itself expanded at different rates. Each transition was preceded by a period of relative uniformity, a smoothing of fluctuations. The cosmic microwave background, the faint afterglow of the early universe, shows this with astonishing clarity. Tiny variations frozen into space reveal a universe that paused balanced on a knife edge before choosing the structure we now inhabit. Silence is written into the sky. But what does any of this have to do with human experience? After all, we are not electrons or early universes. We are biological systems, warm, wet, and noisy. And yet, we are also physical systems embedded in these same fields. Our bodies, brains, and environments obey the same laws. We are not separate from the universe. We are arrangements of it. The human brain is one of the most complex physical systems known. It operates at the edge of chaos, balancing stability and flexibility. Too much noise and thought dissolves into randomness. Too little, and it becomes rigid, unable to adapt. But occasionally, the brain enters a state of unusual coherence. Brain waves synchronize. Neural chatter quiets. Attention sharpens. Subjectively, people report this as stillness, clarity, or a sense that something is about to happen. From a scientific perspective, these states are associated with transitions in cognitive models. The brain updates its internal predictions about the world. Old assumptions dissolve. New interpretations lock in. Learning, insight, and decision all require the collapse of possibility into commitment. In other words, the mind experiences its own version of timeline selection. This does not mean that consciousness magically reshapes the universe at will. Physics does not support that claim. But it does suggest that consciousness participates in how reality is experienced and navigated. The observer effect, often misunderstood, does not mean that human awareness creates particles out of nothing. It means that measurement, interaction, and information exchange affect outcomes. Observation is a physical process. When a system becomes highly sensitive to initial conditions, small influences matter more. Near critical points, tiny perturbations can determine large-scale outcomes. In such moments, silence is not emptiness, it is maximum susceptibility. This is why the metaphor of a silent field resonates so deeply. Across scales from subatomic particles to neural networks to cosmic evolution, silence marks thresholds. It marks moments when systems stop exploring and start choosing. Historically, science has been cautious about extending these ideas beyond their proper domains. And rightly so. There is no evidence that individuals can consciously jump between literal parallel universes. But there is strong evidence that complex systems, including human lives, undergo nonlinear transitions. Careers change suddenly. Relationships end abruptly. Belief systems reorganize overnight. From the inside, these shifts feel dramatic and personal. From the outside, they often follow long periods of apparent stagnation. Nothing seemed to be happening, and then everything changed. In physics, this is called a bifurcation. A system reaches a point where its current trajectory becomes unstable. Multiple futures are possible, but only one will be realized. Noise decreases. Correlations increase. The system commits. If we describe life paths as timelines, not in a mystical sense, but as sequences of states unfolding over time, then timeline shifts are simply moments when the governing dynamics change. New constraints appear. Old feedback loops break. The future reorganizes. What makes these moments so unsettling is their quietness. Popular culture teaches us to expect transformation to be loud and dramatic. But science tells a different story. The most important changes often arrive without warning, preceded not by chaos but by calm. This has implications for how we interpret our own experiences. Periods of stillness, boredom, or emotional flatness are often dismissed as unproductive. But from a systems perspective, they may indicate proximity to a transition. The absence of signal may mean that the system has exhausted its current patterns and is preparing to reorganize. This does not guarantee a positive outcome. Transitions can lead to stability or collapse. Ice can freeze or shatter. Stars can ignite or implode. Silence does not promise improvement. It promises change. Understanding this reframes how we think about agency and fate. We are not passive passengers in a deterministic machine, nor are we omnipotent creators of reality. We are participants in a universe that balances randomness and structure. Our actions matter most when systems are sensitive, when the field is quiet enough for small inputs to have large effects. This is why timing matters in science and history and in personal decisions. Acting too early when noise is high dissipates effort. Acting too late after a transition has locked in changes little. The critical moment lies in between in the silence. Physicists search for these moments using mathematics and instruments. Economists look for them in markets. Ecologists watch for them in ecosystems, and neuroscientists study them in the brain. Across disciplines, the pattern holds. When variability collapses, pay attention. The idea that your timeline shift is happening now should not be read as a prophecy. It is a description of a process. It suggests that certain internal or external conditions have aligned, reducing uncertainty and increasing sensitivity. Whether this leads to growth, disruption, or stagnation depends on forces already in motion. Human intuition is built for a world that appears continuous. We expect causes to produce effects smoothly, one after another, like gears turning in a clock. But beneath that comforting illusion, physics tells a different story. At the deepest levels, reality does not flow, it jumps. And those jumps are governed not by certainty, but by probability. In classical mechanics, probability is a placeholder for ignorance. If you do not know the exact position and velocity of a ball, you use statistics. But the ball itself always has a definite state. Quantum mechanics shattered that assumption. At the quantum scale, probability is not a reflection of incomplete knowledge. It is the fabric of reality itself. Particles do not have definite properties until interactions force them to. Before that, they exist as distributions of possibility. This distinction matters because it reframes how change occurs. In a probabilistic universe, the future is not a single line extending forward. It is a landscape of potential outcomes, each with its own likelihood. What we experience as a continuous timeline is, at a deeper level, a sequence of resolved probabilities. When physicists describe the evolution of a quantum system, they do not track a particle moving through space like a marble rolling along a track. They track a wave function, a mathematical object that encodes all possible states the system could occupy. Over time, this wave function evolves smoothly according to precise equations. But when a measurement occurs, that smooth evolution ends abruptly. The wave function collapses. One outcome becomes real, the rest disappear. This collapse is one of the most debated features of modern physics. Some interpretations treat it as a real physical process. Others argue it is simply an update of information. Still others, like the many worlds interpretation, suggest that all outcomes occur, each in a separate branch of reality. Regardless of interpretation, the empirical facts remain the same. Probabilities govern what can happen. Observation determines what does happen. And crucially, the transition from possibility to actuality is not gradual. It is sudden. This suddenness is what gives rise to the sensation of timeline shifts. When a system moves from one regime of behavior to another, it does not always pass through intermediate states we can perceive. Instead, it crosses a threshold. On one side, many futures are open. On the other, only one remains. In everyday life, this is easy to overlook because our experiences are coarse-grained. We do not perceive the microstates of our environment. We see averages. But occasionally, the underlying discreteness of change becomes visible. A decision that felt impossible suddenly feels inevitable. A situation that seemed stable collapses overnight. A new direction appears fully formed, without warning. These moments feel discontinuous because they are. In the history of science, this pattern appears repeatedly. Scientific progress is often portrayed as a steady accumulation of knowledge. In reality, it advances through abrupt shifts in understanding. Thomas Kuhn famously called these paradigm shifts. For long periods, a dominant framework explains observations well enough. Anomalies accumulate, but they are ignored or explained away. Then, suddenly, the old framework can no longer hold. A new model replaces it, reorganizing facts that were always there but previously made no sense. From the inside, these moments feel like confusion followed by clarity. From the outside, they look like revolutions. In both cases, there is a preceding silence, a period where the old explanations lose their power, but no new ones have taken their place. The field becomes quiet because the existing patterns have exhausted themselves. Probability theory offers a useful lens for understanding this. In complex systems, outcomes are shaped by distributions rather than single causes. As conditions change, the shape of the distribution changes. Possibilities that were once unlikely become dominant. Others fade away. Near critical points, the distribution narrows sharply. The system becomes less exploratory and more decisive. This narrowing is the mathematical counterpart of silence. Consider a system with many degrees of freedom, such as a climate model or an economy. When external conditions are stable, the system explores many states. Fluctuations are common. Predictions are uncertain. But as constraints tighten, behavior becomes more predictable. Variance drops. Correlations increase. The system locks into a pattern. This does not require consciousness or intention. It is a natural consequence of how probability works under constraint. But when such processes occur in systems that include human perception and decision-making, they acquire psychological significance. The brain itself operates by predicting the future. According to predictive processing theories, perception is not passive reception of sensory data. It is active inference. The brain continuously generates models of the world and updates them based on incoming information. When predictions match reality, neural activity is minimal. When they do not, error signals increase, driving learning and change. Silence, in this context, can mean two things. Either the brain's predictions are perfectly aligned with experience, or the system has temporarily suspended prediction, awaiting a reorganization. In both cases, noise decreases. Neuroscientific studies of decision-making reveal that choices are often made before conscious awareness catches up. Neural activity ramps up toward a threshold, then suddenly stabilizes. The subjective experience of deciding follows the physical commitment. From the inside, it feels like a sudden realization. From the outside, it is the end of a probabilistic process. This undermines the comforting idea that we consciously steer every outcome. But it also reveals something more interesting. The moments that matter most are not the ones filled with frantic thought. They are the ones where uncertainty resolves. In a probabilistic universe, continuity is an illusion created by scale. At small scales, events are discrete. At large scales, they blur together. But when a system crosses a threshold, discreteness breaks through. Change becomes visible. This is why so many cultures, independently, have developed metaphors of crossing, awakening, or shifting. Long before modern physics, humans noticed that life does not always progress smoothly. There are moments when everything feels different, even if nothing obvious has changed. These moments are often preceded by a sense of emptiness, stillness, or suspension. From a scientific perspective, these experiences can be understood as transitions between stable states in a complex system. The language of timelines is metaphorical, but the underlying process is real. It is important, however, to resist the temptation to overextend the analogy. Physics does not support the idea that every subjective feeling of stillness corresponds to a literal branching of universes. Most changes are local and contextual. They occur within a single physical reality governed by consistent laws. But within those laws, there is room for multiple futures. Probability does not eliminate causality. It reshapes it. Causes do not guarantee effects. They bias outcomes. And when biases accumulate, they can suddenly dominate. This is where urgency enters the picture. In a system approaching a transition, timing matters. Small actions taken at the right moment can have outsized effects. The same actions taken earlier or later may do nothing at all. This principle is well known in control theory and engineering. Systems are most controllable near points of instability. Far from those points, they resist change. Near them, they amplify input. In human terms, this means that periods of apparent stagnation are not necessarily wasted. They may be periods of preparation, where the system's internal parameters are shifting invisibly. When the transition arrives, it may feel sudden, but it has been building for a long time. The danger lies in misinterpreting silence as emptiness. In a probabilistic framework, silence often means that variability has collapsed, not that activity has ceased. The system has stopped exploring because it is about to commit. This reframes how we think about control and surrender. There are moments when effort increases noise, pushing a system away from a threshold. And there are moments when restraint allows probabilities to narrow naturally. Neither approach is universally correct. The challenge lies in recognizing which phase you are in. Physics offers no simple rule for this, but it does offer a warning. When a system becomes unusually quiet, when fluctuations die down and patterns simplify, change is imminent. Whether that change is constructive or destructive depends on the structure of the system and the forces acting on it. In the universe, silence precedes both creation and collapse. Stars form when gas clouds cool and turbulence decreases, allowing gravity to dominate. Stars die when nuclear reactions quiet, allowing gravity to overwhelm internal pressure. In both cases, stillness marks the tipping point. The same mathematics describes these processes. Differential equations governing stability, energy flow, and constraint. There is nothing mystical about them, but their implications are profound. If reality is structured by probability, then the future is not written in advance. It is shaped moment by moment, narrowing from possibility to fact. The sensation of a timeline shift is the subjective shadow of that narrowing. Understanding this does not grant control over the universe, but it offers clarity. It suggests that the most important moments may not announce themselves with drama. They may arrive quietly, disguised as nothing at all. Time feels obvious. It moves forward. The past is fixed. The future open, the present a thin line we slide along moment by moment. This intuition is so deeply embedded in human experience that it rarely feels worth questioning. And yet, modern physics has been quietly dismantling this picture for over a century. What it has replaced it with is stranger, colder, and far more unsettling. Time, it turns out, may not flow at all. In Einstein's theory of relativity, time is not a universal river carrying everything forward together. It is a dimension inseparable from space, forming a four-dimensional structure known as space-time. Events do not move through time. They exist within it. Past, present, future are not absolute categories, but relative ones dependent on the observer's motion and gravitational environment. What feels like the present to one observer may already belong to the past or future of another. This alone destabilizes the idea of a single, objective timeline. But relativity does not stop there. In many solutions to Einstein's equations, the universe is best described as a block, a complete structure containing all events that ever happen. In this view, time does not pass, it simply is. The sensation of flow arises from how conscious systems process information, not from the structure of reality itself. If this sounds abstract, its implications are concrete. In a block universe, change is not the creation of new moments, but the traversal of a pre-existing structure. The future is not coming into being. It already exists, just not here. Quantum mechanics complicates this picture further. While relativity treats spacetime as fixed, quantum theory introduces indeterminacy. Outcomes are not fully specified until interactions occur. The future, in this framework, is genuinely open, described only by probabilities. Reconciling these two views remains one of the central challenges of modern physics. Some proposed solutions suggest that reality is neither a static block nor a continuously unfolding process, but something in between. Time may be emergent, arising from deeper, timeless laws. Causality may be local, not global, and what we call the present may not be a point but a boundary, a surface where possibilities condense into facts. This is where the language of timelines becomes useful again, not as a literal map of parallel worlds, but as a way of describing how different futures are embedded within the present. At any given moment, multiple outcomes are physically allowed. The structure of the universe constrains them, but does not select among them. Selection happens through interaction. In physics, interaction is everything. Particles interact. Fields interact. Systems exchange energy, momentum, and information. Without interaction, nothing happens. But interaction is also what destroys superposition. It is what forces a system to choose. From this perspective, the present is not a moment in time. It is a process. It is the act of resolution. When people describe a sense that everything suddenly feels different, what they are often experiencing is not a change in external conditions, but a change in how those conditions are integrated. The underlying variables may have been shifting for a long time. Then, at some point, the system crosses a threshold. The old description no longer applies, a new one snaps into place. In physics, thresholds are everywhere. Phase transitions, event horizons, stability limits. At a threshold, small changes stop producing small effects. The rules reorganize. Time behaves differently near thresholds. In dynamical systems, evolution slows near critical points. In cosmology, time dilation occurs near massive objects. In subjective experience, moments of crisis or insight often feel stretched or suspended. The clock keeps ticking, but perception detaches from it. Silence appears again here, not as the absence of sound, but as the absence of narrative. The familiar story of what is happening dissolves. The future no longer feels like a continuation of the past. It feels undefined. This undefined quality is deeply uncomfortable. Human cognition is built to predict. When prediction fails, anxiety rises. Many people interpret these moments as emptiness, loss, or stagnation. But from a physical perspective, they may be something else entirely. They may be moments when the system has reached the limit of its current description. The universe does not guarantee continuity of meaning. It guarantees only consistency of law. This distinction matters. Laws constrain what can happen, but they do not specify what must happen. Within those constraints, outcomes are shaped by initial conditions, interactions, and chance. When systems are far from thresholds, change is gradual and predictable. Near thresholds, It is abrupt and opaque. The idea that a timeline can shift is best understood in this context. It is not that reality fractures and recombines. It is that the governing dynamics of a system change. New variables become relevant. Old ones lose influence. The effective future reorganizes. From the inside, this feels like entering a different world. From the outside, it is a phase change. One of the most persistent misconceptions about physics-based discussions of consciousness and reality is the belief that intention alone drives outcomes, that if one simply observes or desires strongly enough, the universe will comply. This idea borrows language from quantum theory while ignoring its constraints. Observation in physics is not passive awareness, it is physical interaction. Measurement devices disturb systems. Environments decohere states. Energy is exchanged. There is no mechanism by which thought alone selects outcomes independent of physical context. And yet, context includes the observer. Human actions are part of the causal network. Decisions change environments. Attention shapes behavior. Behavior alters future constraints. While consciousness does not override physics, it participates in it. It is one of the processes through which interactions occur. This is where urgency enters the picture one final time. In systems approaching a threshold, influence is asymmetric. Some inputs matter far more than others. Timing outweighs magnitude. Alignment outweighs force. Silence, then, is not a command to act or not act. It is a signal that the system is sensitive. In cosmology, the early universe's silence after inflation allowed structure to form. In geology, stress accumulates silently before earthquakes. In biology, genetic mutations lie dormant until environments change. In each case, the visible event is only the final step of a long, quiet preparation. The same is true of human systems. Societies appear stable until they are not. Technologies mature unnoticed until they transform everything. Lives drift until a single decision locks in a new trajectory. These are not miracles. They are thresholds. The unsettling implication of this view is that certainty is always retrospective. Only after a transition do outcomes appear inevitable. Beforehand, they are genuinely open. This openness is not a failure of prediction. It is a feature of reality. When the field goes dead silent, it is not offering reassurance. It is withdrawing noise. It is stripping away distraction. What remains is structure, constraint, and possibility narrowed to a knife edge. Whether that edge leads to growth or collapse depends on factors that may be partially outside awareness. But awareness itself is not irrelevant. It is part of the system's feedback loop. This is why the experience of silence often feels meaningful, even when its meaning is unclear. The brain, evolved to detect change, recognizes the pattern. Something is about to reorganize. The universe does not announce its turning points with certainty or explanation. It announces them with stillness. In this sense, the idea that your timeline shift is happening now is neither prophecy nor superstition. It is a description of a universal process playing out at a human scale. A system has reached the limit of its current configuration. Variability has collapsed, the next state is forming. There is no guarantee of what that state will be. Physics offers no promises. It offers only patterns. And the pattern is this: the most profound changes do not arrive with noise. They arrive when the field falls quiet, when time feels thin, when the future stops behaving like an extension of the past. That silence is not the end of motion. It is the boundary between what was possible and what will be real. And once crossed, there is no going back.